started last time. So we derived it, and let me repeat it here. Simpsons rule for a function f with the interval h equals to this guy, h over 3, f x0, f x 2n, and then you have to sum over all the odd ones, odd indices, right? So I from 1 to n, if I write to I minus 1, all the odd ones are multiplied by 4, and all the even ones are multiplied by 2 to I, and that will be I from 1 to n minus 1. Okay. So be careful, very, very careful with all these indexes. Always double check if you get them right, because that's what it's all about when you sit down and write a code. You have to make sure all the indices are correct, otherwise you'll never spit out the right answer, right? So always be careful. Okay, so what we're going to do today is I will give you a sample code of how to code this in Matlab, all right? So a sample code. Okay. So assuming the following things are given, so somehow you already have assigned value to A, to B, and to n, or you can say those might be the inputs. You can make this into a function if you want. These are given, and also this function func is given. Your function is already defined over there. Okay, so let's see how can you write this inefficient code. So you see I need the age, so let's first compute the age. So here's your script. Write it as a script right now. So h is, by definition, b minus a divided by 2n. Is that right? So divided by 2 divided by n, whichever way you want. You can put a bracket and say 2 times n. Okay. And then I see, and this is actually a one-line algorithm, and I do not want to write a for loop for these sum. What I will do will be using the Matlab program called sum, just to sum it up. I write it in a vector. Okay, so then I need to get a hold on a vector that contains all the odd indexes for x. Okay, so I'm going to construct an x odd, which simply contains all the odd grid points for x. Is that clear what I'm doing? So I know this will be, what will be the first grid point here, x1? It will be a plus h. Is that right? That's x1. And then after that, between two odd points, the distance of them will be 2 times h. Is that clear? This is the same as the command line space. Okay? I prefer this one. It's clearer for me. And then what will be the last one? Well, it doesn't end at b because it's a b will be indexed to n, right? So it's one less, so it's b minus h. Is that clear? Just that line gives you a vector of all the odd x's are there. Is that okay? Yes? No? With this information given, can someone tell me how can I construct a vector for all the even inner grid points? So what will be the first point? Is it A? Of course not. A is at the boundary. So what should I add to get x2?
2h.
2h. Will this pass Matlab inspection?
No.
No. I have to do this. Is that right? And it jumps, the distance between two neighboring ones is again 2h. And when should it be ending? It's not b, right? B is the boundary, so it's 2h away from b, smaller, right? Minus 2 times h. Is that clear? That's the vector containing all the even inner indices of x. Okay? Now you can write out your s. Let's say s, capital S, will be the value for the Simpsons rule. You can just read through and write it up. So I will be having h divided by 3 multiply by f. Okay, it's not f, it's func. I don't know why I choose func. It's so much shorter if I just choose f. Func a plus func b, right? Plus 4 times sum of your function func evaluated at x odd. Is that right? You see, you're just reading this and type it in the Matlab. So 2 times sum of func x even. Now I have to count how many brackets. 1, 2, 3. In Matlab, it will light up the one corresponding to the one you type in so you don't mess up. Okay, semicolon, so you don't want all those displays. And that's it. Is that okay? So that's what you need for your homework problem. There is a programming problem for the Simpsons rule, and the codes are just here. You can just use it. I have no objection. Okay? All right, if that's okay, we go to our favorite topic, error estimate. We always have to know what will be the error. So you know this can be derived in a totally similar way as for the trapezoid rule, but here is Simpsons rule. So on each subinterval, you are fitting in a quadratic polynomial that interpolates 3 points, right? Trapezoid rule will be a linear polynomial. So it's totally in the same way. So let's take a look at the local error. That means the error on one subinterval, and let's denote it by arrow for Simpsons rule on interval number I with the function f with the length h. Okay, that's our standard notation. So one can show that it equals to the following. Okay, for some psi I on the interval from x to I plus somewhere there. Okay, so the derivation for this formula is very similar to the one we did for the trapezoid rule. So it's a bit bigger, it's more work. There's an integral of a cubic polynomial to integrate. Okay, so the detailed proof for this is in the lecture notes, and I choose to skip it. I encourage you to read it and or maybe work it out on your own to see if you can get this. Okay, is that okay? It would take 15 minutes if we go through it. So, well, in the end, that's what we have. So remember, this is h to the 5th. That's actually a very high power. So let's look at the total error by using this. So error for Simpsons rule, the total error is nothing but the sum of this over all I. So I'm going to play the same trick as we did. So it's not so miraculous anymore because you know I played it last time. So for this expression here, I'm going to multiply it by identity 1, and I'm going to write the 1 in a fancy way. The 1 will be 1 over n times b minus a times 2h. That's 1 altogether. Is that okay? You've seen that, right? And then I'm going to combine these two together. So I think 1 over m times that summation is something. So do we remember what will be this guy here? What does it represent? Some average value for the fourth derivative, right? Assuming f fourth derivative is a continuous function, then this would equal to f fourth derivative of some psi. Okay, by intermediate value theorem. So for some psi on the interval from a to be. It holds. It exactly equals to it. Okay, so let's get rid of the 1 of the power. So I get a 4 here. You can join the 2 with that 90. You get negative 1 over and 180. And this f to the 4th derivative of some psi times h to the power 4. Is that okay? That's your error estimate. Okay, so for some psi on the interval from A to B, exactly where we don't know, but we know it exists. So a more useful bound, a more useful thing will be an error bound. Because I don't know the psi, so it's not very useful. Question?
Where did the B minus A go?
Oh, I don't know. I threw it in the garbage. There's a B minus A, of course. Thank you. Okay. Oh. You okay? So we take absolute value for the arrow. You know, if you try talk and write at the same time, either you say lots of funny stuff or you write lots of funny stuff. Because your brain, it's hard to keep track of 2 things, really. You should try it.
Oh, I don't want to.
You should. Okay, so arrow bound, I take absolute value, and then I find the maximum of this guy. It's some property of my function, right? So I get b minus a over 180. I do have b minus a in my notes, so I was not looking at my notes. So max of f 4th derivative of some psi. Well, okay, for any psi. I could just change it into x, but it doesn't matter. H to the 4th. That's your arrow bound, and this is something that you can figure out. It's a property of your function, right? Given function, given interval a and b, you can find that value. So tell me, what's the order of this method now? Where do you find that order? 4. Wow, that's the first to 4th order method. So, do you understand how powerful that is? What a huge difference it would make jumping from 2nd order to 4th order. I'll show you in the next example. This is a continuation of example 2 for the trapezoid rule. Okay, so now we want to compute an integral using Simpsons rule, and I want some error tolerance. And the question will be, how many points at least must I take? All right, so the same thing, let me pull this up. I want to compute the integral from 0 to 2 e of x dx, okay, by Simpsons rule with the arrow shall be less than equal to, let's put the same tolerance, 0.5 10 to the negative 4, okay? And I want to find out what is the minimum number of points. Of course, the more points you take, the more accurate it will be. Okay, what is the minimum? So this will be met. Okay, so we will follow the same line of computation. So you know you use your arrow bound. So all you need to figure out is this guy here, right? Then you can throw in. So what is this guy? Well, we know any derivative of the exponential function is the exponential function. What would that be? So a is 0 and b is 2 for my problem, right? And that's e to the x. So we already know from last time that's e squared. Is that right? So throw that in the arrow bound and say the right-hand side is bounded by your tolerance. So we must require the following. We need the following. So b minus a is 2 over 180 shall be times, that one is e squared times h to the 4th shall be less than equal to 0.5 times 10 to the negative 4. Is that right? So anybody remembered how many points it was needed using trapezoid rule just last class?
300.
300 something? Yeah, okay. What do you expect here? Maybe 100?
Square root of 100.
25?
Yeah.
Okay, no, square root it's 10.
So on that order.
Oh, so you're taking 300, you're taking square root of it. Why is square root of 100?
Because the last order was second order, so it's
H is,
for that you get a fourth order method.
so you just take square root about 300, right?
Yeah.
Okay, what would that be? 15
10 times square root of 3.
Yeah, okay, 17. Square 3 is 1.732. Sorry. Okay, so let's see if his prediction is close. So let's do h to the 4th. Now, the leading coefficient is a little bit different, though. So it's slightly different. So you're pretty close to it. So I move this over, I multiply by 90, and multiply by e to the -2, right? So I work this out, it approximately gives me, the calculator gives me 1.218 times 10 to the -3. Okay, and then you take 4th root, and then you know take 4th root, h will be less than 4th root of that is about 0.18682. Okay, so what is my h related to n? So h equals to b minus a over 2n, isn't it? So it's b minus a, 2 minus 0 over 2n. That's my h, less than 0.18682. Okay, so that's just 1 over n, so n shall be bigger than equal to, okay, something like that, and then you hit your calculator. This gives me something about 5.3, but I want a whole number, so I'll bump it up to 6. Is that okay? N equal to 6, so what is n? N is the number of subintervals, right? What is the number of points? n is number of small subintervals, and you have extra end point to it. Is that right? Okay, so 13, pretty close. Okay, so now if you use Simpsons rule, well, the method will be a little bit more involving. You have to be careful, the even index, odd index added up in a different way, but you see it's nothing complicated, that code. 3 lines, we're done with it. And you can reduce a computation involved over 300 points down to 13 points. Dramatically change, right? Do we agree? This is much more powerful, okay? Is that okay? All right. So later on we will look at some other methods, Gaussian quadrature, but that comes later. So we'll take a break from this method and take a look at some more, how do you say, more advanced algorithm, that recursive. Okay, so I want to introduce you to something called a recursive rule. And it's just a way of thinking. So you could apply it to Trapezoid or to Simpson, to many of these methods. To fix the idea, we'll introduce it for the Trapezoid rule, but it's not restricted to it, okay? You see, the idea is pretty much you can apply to many things, okay? So this is also has another name, also called Composite Rules. Composite, okay, schemes, rules, they're the same thing. Okay, so I have an interval from A to B, which is interval you integrate a function. We're always doing the same thing here. So I will cut it now into slightly different. So I will cut it always into powers of 2. See, powers of 2 always comes in this class. So let's say 2 to the power m equal, remember it has to be equal, subintervals. I cannot write. Okay, so let's see, m equals to 1. Let's draw a couple of these graphs. Let's see, that's from A to B. M equals to 1. That means I cut it into 2 subintervals, right? And if I bump the m up by 1 more, m equals to 2, what do? Well, I will cut it into 2 to the power 2, 4 subintervals. So what do will be, I keep the previous division and go into each subinterval and cut it further up into 2 pieces. Do we see that? Each time I have twice as many subintervals as the previous round if m increased by 1. Okay, so m equal to 3, let me draw another one. So I will copy the previous one, and then I will cut each subinterval in half. Is that clear? Let's do one more round. M equals to 4. Oh no, should not do that round. This is gonna drive me crazy. Okay, that's the copy, and then I cut it further. Okay, pretty uniform. Okay, I said, pretend it's uniform grid. Is it clear, the idea? So we keep doing this, okay? And then for each of this, I will compute the trapezoid rule using that grid. Okay, so I compute the trapezoid rule here, and here, and here, and here. Maybe I have 10 levels of such, then I have 10 numbers. Okay? Let's see. Okay, let's set up some notations. I need to write now h, m. The length of the interval at level m, what will that be? Well, that would be b minus a over the total number of subinterval, which is 2 to the power m. Is that right? Okay, and then between the 2 neighboring levels, the length of h is exactly halved if you increase m by 1, because you cut them further into all half. Is that right? Okay, so now I'm going to write out the trapezoid rule at level m. The trapezoid rule T for the function f using hm. Okay? Okay, this is just trapezoid rule, so let me write it out, hm. And I will have a half f at A plus a half f at B plus, have to summing over all the inner points. So f at all the xi's that are inner, so I can write it as A plus I times hm. These are the xi's, all right, at that level. So I run from 1 all the way to n minus 1. My n here is equals to 2 to the power m. So this is 2 to the power m minus 1. Is that okay? Index, okay, have to be clean with index, not messing up. Okay, now after computing that, I decided to compute one more level. I increase m by 1. Okay, so let me write this out. So this gives me h m plus 1. I'll just write out as it is, and then we'll look at it. fa and half f of b plus, it's the same thing except I have to change m into m plus 1, right? So summation, I from 1 to 2 to the power m plus 1 minus 1 f of a plus I h m plus 1. Is that okay? h m plus 1 is half of h of m. Okay? Okay, so we can probably go back and look at the graph, which may be easier. See, between 3 and 4, if you increase m by 1, what happens to your grid? You know, in the trapezoid rule computation, all the points that existed at the previous level are still there at the next level. Do we see? Including the 2 boundaries. Okay, two boundaries we'll treat separately. It's always there. The two boundary parts are the same. It's always there. And in the two brackets, that summation here actually contains two parts. One is all the points coming from the previous level. And then there's the other part that are the newly added ones. Do you see that? This will be x1 at this level. This will be x3. This will be x5. So there will be all the odd index. Okay, so that's what I'm going to write. So I use this hm is hm over 2. I'll have a half fa and a half fb. Okay, so I'll break this summation up into two parts. So one part will be all the points that's already used in the previous level. So I from 1 to 2m minus 1 fa plus I hm plus, and then all the points that is not included, the newly added one, meaning the odd index one at the level m plus 1, right? Okay, so that will give me f of a plus. So I want to figure out what are these xi's. Well, that will be the length here is h at m plus 1 and all the odd indexes. So they are, the odd indexes can be represented by something like 2i plus 1, and you let I run from 0 to n. That gives you 1, 3, 5, 7. Is that clear? So that's the one I'll be using, and then h m plus 1. Right? In the bracket. And then this I runs from 0 to m minus 1. So when I is 2m minus 1, you are exactly the second last point right there. You can verify it. Okay. So now we see, let's look at all these terms here. So provided TF at HM is already computed, do I need to recompute this part? No, it's here, isn't it? It's in the bracket, right? So multiply by HM, that's exactly this guy. So I will have a half T of FHM coming out, isn't it? You just need to multiply by half, okay? And then I have, of course, the newly added one. You have to go through them. So let me write it over. So this I'll write as HM plus 1. HM over 2 is HM plus 1. And then I do the summation. I'll just copy. Is that clear? So in this computation, once you kind of refined your grid, you cut all the subinterval into half, and you double the total number of intervals, you don't have to throw away the previous computation. You could use the previous computation. You only need to evaluate your function at the newly added points. Is that clear? So you know, we always care about computational efficiency, so we know the function evaluation is the most expensive procedure. Okay, so this one will not make you do one extra function evaluation unnecessarily. Okay, it's very, very, very sharp. Do exactly what you have to do. Okay, so let's take a look at some advantages. What can you think of some advantages for this algorithm? Why would it be useful? In what situation? Oh, it's totally useless. Is it useful? Say you cut your interval into 16 pieces and you throw in trapezoid rule and you find some answer. And then you checked and you think there's too big error. You want to refine it. What would you do? Would you, will this be helpful in some sense? So you could cut each subinterval into 2. Is that right? And then you do this kind of a recursive formula, then whatever you have computed should not be thrown away. You can build it on top of that. Do we see? So, 2 aspects in that. One is flexibility with respect to arrows, right? So you could add, just add, well, not really add, so cut subinterval into 2 pieces, and you can do this composite scheme, and you can have a rather and to improve the accuracy. Okay, so it's flexible, and you could, and then after that, if it's still not good enough, you can take one more step, right? So allow you to kind of fine-tune your result, and also in the process, you never waste extra computational time by doing unnecessary function evaluations, right? So I have to say, it's also pretty efficient. Okay. Okay, so it's pretty nice, something that allows flexibility and some efficiency. Okay, so, but I want to tell you that's not the end of the story. This is just one little piece that will eventually go into something much bigger. Build on top of that, you can have something really, really powerful. Okay, so let's get into that a little bit. So the algorithm eventually is called the Romberg's algorithm, and it's built on top of a little, really not that big, a little idea which I'll represent to you, and it carries the name of Richardson. So this is something called extrapolation. So Richardson's extrapolation, okay, versus interpolation. You extrapolate, you go outside the interval of your information and try to predict outside. Okay, so let's see. So the starting point is that I have a bunch of these. So let's say given trapezoid rule. So this extrapolation again is not related to trapezoid rule. So I present it in trapezoid rule, and you see that it can be applied in many situations. Okay, so given, let's say, these computation of trapezoid rule, f with certain h, and then you halve the grid size, and you have another one, and let's say you halve the grid size again, you have another one. Let's say you have a couple of them, 3, 4, 5, maybe 8 of them. Okay, given that, can you come up with some idea? The basic idea will be, well, I know that's a second order method. Okay, so can I just use them in a smart way to get something really higher order? Really higher, okay? So let's see what one can do here. So the key element here is actually the information on the arrow. So you should have some arrow analysis. Usually it holds, and sometimes it doesn't hold for some functions, but still the method would work. So assuming now your arrow for the trapezoid rule follow the following. So arrow analysis for trapezoid. Let's see, the arrow E here with function f with the interval length h, that will be the integral of f minus your trapezoid rule with length h. Okay, so I'm not going to prove this, so I have to say assume this holds. Okay, let's say, but one can prove it. So a2 h squared plus a4 h fourth plus a6 h6 plus dot, dot, dot. So this is called the, this has a name, Euler-Maclaurin formula. I don't know if you have heard of it. Anyone heard of that? Euler-Maclaurin formula? No, maybe not. I think it's only in numerical analysis, probably. So one can obtain this formula just by Taylor series of the method, okay? And these AIs, these ANs, are related to the nth derivative of the function f, the maximum of it on the interval, multiplied by some constant. Okay, so these are actually constant with respect to h. They don't depend on h. Okay, and because of the symmetry of your method, you only get the even power of h terms. There's no odd ones. They exactly cancel each other. Okay, so that allows actually a very strong result in the end. Okay, so assume this holds, and we're gonna manipulate it and get something unbelievably strong. So, okay, so if I have this for arrow for interval length h, what about for this trapezoid approximation with h halved? What will be the arrow? Well, if this holds for this h, then it holds for h half, right? You just change all the h into h half. Is that clear? Same constant a2, h half square plus a4, h half to the fourth plus a6, h half to the sixth plus many terms, as many terms as f can be differentiated. Okay, so I see we know trapezoid rule is a second order method. That's why that's the leading arrow term, which is h squared, and this is the leading arrow term, is h squared divided by 4. It's still h squared. So here comes the main idea. Using those two equations there, is it possible that I manipulate it such that I get rid of the leading arrow term, that it disappears after I manipulate it in some way? Is it possible to cancel the leading arrow term? Meaning the term with h squared. What do you think? What can I do? Let's call this equation 1 and the second one equation 2. If I subtract the two equations, will this term be gone? This is a2 actually times h squared over 2 squared, right? If I subtract them, will this arrow be gone, the first one? What can I do that it's gone?
You can divide.
Divide the two equations? How? Multiply this by 4, then subtract. Yes. Do we see that? And that's just that little idea. That's the extrapolation, okay? Not such a big idea, right? So take equation 2, multiply by 4, and then subtract equation 1. Okay? So I do not want to write it 4. I want to write it 2 squared because that's not the only step we're going to take. Okay? So so in these two equations, I don't know the arrow, and I don't know the arrow. If I know the arrow, I can add it on top of t and I get I, right? So the arrow I don't know, and this is the thing I'm trying to approximate, right? And I have this value and I have this value. So these two values are computed, okay? So keep that in your head, okay? And these are analysis. Okay, so if I multiply this by 4 and subtract it, so I would not have this arrow term with me. I'll multiply this by 4 minus that, multiply this by 4 minus that. Okay, so what I will have will be 2 squared minus 1 times I of f minus 2 square t f h half plus now t f h equals 2. So I know the first term will cancel each other, these two terms, because the way I manipulate. And what happened to this term, it's some number times h to the 4th, and this will be a4 over 4 times h to the 4th, so resulting in 3/4 of a4 h to the 4th. But it's some constant times h to the 4th, so I'll denote this as a tilde for h to the 4th. Is that okay? I don't specify what exactly it is. It depends on a4 in some way. It's a constant. Okay, it's a new set of constant. And then I will have a6, h to the 6th, and so on. Is that okay? These are just another set of a's. Okay, so I want to find an approximation to this guy. So can I write this on the left-hand side, move everything else to the right-hand side? Let's do that. So I of f now equals 2. I move these over, so I get 2 square t f h half minus t f h over 2 square minus 1, right? And then all these terms will be divided by 3, right? This will be a tilde 4 divided by 3. It's another constant. Let's just call it a4 bar. Okay, I could just don't bother and just write it as a4 because these are constants. It's the h that matters for some an bars. Is that okay? So what is the leading arrow term now if I approximate my integral by this guy? Let me stick to the same notation. I call this u of h equals to that. If I take the 2 trapezoid rule result and just do this in this manipulation, multiply this by 4, subtract, divide by 3, 3 more flops of computation can be done like nothing, right? What do I get? What is the leading arrow term? H to the 4th. That's the dominating term, right? You get this guy here becomes a 4th order approximation. Wow, that's the same as Simpsons, isn't it? Simpsons is only 4th order. All I did is I save the previous trapezoid result, and then I do this manipulation. It bumps up 2 orders. Is that clear? So, yeah. We'll stop here because next will be the derivation of the Romberg method. So you see that I don't have to stop there. Do you see? Once I have a bunch of these UH's, I can compute a UH and I can compute a UH half, and I can do this manipulation again, right? Do you see it? Okay, and we'll talk about that next time, and we'll build up this Romberg algorithm.